Welcome to this problem walkthrough. Today, we'll be exploring LeetCode problem number 1636, titled Sort Array by Increasing Frequency. This problem challenges us to sort an array of integers based on the frequency of their occurrences in ascending order. It's a great exercise to practice sorting techniques and efficient data handling. Let's dive in. The problem asks us to sort an integer array, nums, based on the frequency of each value. Here, the sorting needs to be done in increasing order of frequency. In cases where two or more values have the same frequency, we sort those values in decreasing numerical order. The final output is the sorted array matching these rules. For example, if the input is nums equals 1 1 2 2 2 3, the output will be 3 1 1 2 2 2. This is because the value 3 appears once, 1 appears twice, and 2 appears 3 times. Sorting by frequency in ascending order, we get 3, then 1, and finally 2, maintaining the decreasing order for values with equal frequency. In the first example, the value 1 appears 2 times, 2 appears 3 times, and 3 appears 1 time. Sorting by frequency in ascending order gives us 3 first, as it has the lowest frequency, followed by 1 with a frequency of 2, and then 2 with a frequency of 3. Since there are no ties in frequency, we directly follow the frequency order, resulting in 3 1 1 2 2 2. In the second example, nums equals 2 3 1 3 2, the frequencies are 1 appears once, 2 appears twice, and 3 also appears twice. We first sort by frequency, so 1 comes first. For 2 and 3, which have the same frequency, we sort them in decreasing order of value, placing 3 before 2. This gives the result 1 3 3 2 2. Looking deeper at the second example, after calculating frequencies, we sort the values by their frequency in ascending order. The value 1, with a frequency of 1, is placed first. For 2 and 3, both have a frequency of 2, so we compare their values and sort them in decreasing order. This means 3 comes before 2, giving the final result of 1 3 3 2 2. In the third example, nums equals -1 1 6 4 5 6 1 4 1, the frequencies are as follows: -1 appears once, 1 appears 3 times, -6 appears twice, and 4 appears twice. Additionally, the value 5 appears once. Sorting by frequency, we handle ties by sorting in decreasing order of the values, ensuring the rules are consistently applied. Continuing with the third example, we first handle values with the lowest frequency, which is 1. Both -1 and 5 appear once, so we sort them in decreasing order, resulting in 5 -1. Next, we handle values with a frequency of 2, which are 4 and -6. Sorting these in decreasing order gives 4 -6. Finally, the value 1, with the highest frequency of 3, comes last. Combining these results gives the sorted array 5 -1 4 4 -6 -6 1 1 1. The problem also specifies constraints, such as the array length being between 1 and 100, and the values themselves ranging from -100 to 100. This ensures the input size is manageable and performance is not a concern. Now, let's consider edge cases. For an array with only one element, such as nums equals 5, the output is simply 5, since there are no other elements to compare frequencies. For arrays where all elements have the same frequency, like nums equals 5 4 3 2 1, the output is 5 4 3 2 1, as they are sorted in decreasing numerical order. Another important edge case involves both negative and positive integers. For example, in nums equals -10 10 -10 10 -20, the frequencies are -10 appears twice, 10 appears twice, and -20 appears once. Sorting by frequency, -20 comes first. For 10 and -10, which have the same frequency, we sort in decreasing order of value, resulting in -20 10 10 -10 -10. These examples demonstrate how the rules apply consistently to a variety of inputs. To solve the problem of sorting an array by increasing frequency, we need to tackle two key requirements. First, the elements in the array should be sorted in ascending order of their frequency. Second, if two elements share the same frequency, they should be sorted in descending order of their value. One straightforward way to approach this problem is through a brute force method. In this approach, we manually count the frequency of each element using a nested loop, which has a time complexity of O(n²). After calculating the frequencies, we sort the array based on the frequency and resolve any ties by manually ensuring elements with the same frequency are in descending order. While this approach is simple to understand, it is inefficient for larger arrays due to its quadratic time complexity and lack of scalability. This inefficiency highlights the need for a more optimized solution. A more efficient approach involves using a hash map combined with custom sorting. This method avoids redundant frequency calculations and significantly improves performance. First, a hash map is used to count the frequency of each element in the array. This operation takes linear time, O(n). Next, we sort the array using a custom sort function that prioritizes two conditions, sorting by frequency in ascending order, and for elements with the same frequency, sorting by value in descending order. The implementation of this approach is straightforward, leveraging Python's counter class to compute frequencies and the sort method with a custom key for ordering. The time complexity of this method is O(n plus n log n, where O(n) accounts for frequency counting and O(n log n) for sorting. This approach is both efficient and easy to implement. The space complexity of the hash map approach is O(n), as we need to store the frequencies of all unique elements. This method is advantageous because it is concise, leveraging Python's built-in sorting capabilities and allowing for efficient implementation of the sorting conditions. However, the trade-off is a slightly higher memory usage due to the hash map. Alternatively, we could consider using a bucket sort approach. Here, the idea is to group elements into buckets based on their frequency, with the bucket index representing the frequency count. Once the buckets are populated, we traverse them in ascending order of frequency and collect the elements, ensuring that elements in each bucket are sorted in descending order of value. This approach has a linear time complexity, O(n), for both frequency counting and bucket traversal, making it highly efficient. However, it requires additional space for the buckets and is more complex to implement compared to the hash map approach. One clear advantage of the bucket sort approach is its linear time complexity, which makes it particularly well suited for handling very large arrays. However, the added complexity of its implementation can be a drawback, especially when compared to the simplicity of the hash map and custom sorting method. After evaluating these approaches, the hash map combined with custom sorting emerges as the chosen strategy. This method is straightforward to implement, and it effectively handles both sorting conditions, frequency in ascending order and value in descending order. By sorting based on a tuple, frequency, x, we can seamlessly enforce both conditions in a single step. This insight significantly simplifies the implementation while maintaining efficiency. Overall, this approach strikes the right balance between simplicity and performance. This strategy performs well for most input sizes, offering an efficient and easy-to-maintain solution. While it does require slightly more memory than the brute force approach, the trade-off is well worth the improved time complexity. Additionally, although bucket sort is marginally faster for extremely large arrays, the difference is negligible for most practical cases. The hash map with custom sorting approach is the most practical choice, providing a reliable balance between efficiency, readability, and maintainability. It is easy to debug and scales well for typical problem constraints, making it a robust solution to the problem of sorting an array by increasing frequency. In this problem, we need to sort an integer array, nums, based on two criteria. First, elements should be sorted by their frequency in ascending order, meaning numbers that appear less frequently will come first. If two elements have the same frequency, we then sort them by their values in descending order, so larger numbers will come before smaller ones in these cases. To achieve this, the first step is to count the frequency of each element in the array. For this, we use a hash map, which is called a dictionary in Python. The hash map stores each unique number as a key and its frequency as the value. A hash map is an excellent choice because it allows us to count and retrieve frequencies in O(1) average time. For instance, if the input is 4, 5, 6, 5, 4, 3, the hash map will look like this: 4, 2, 5, 2, 6, 1, 3, 1. Here, the key value pairs represent the number and its frequency in the array. Once we have the frequency of each element, the next step is to define a custom sorting rule. This rule ensures that elements are sorted first by their frequency in ascending order, and if two elements have the same frequency, they are sorted by their value in descending order. To implement this custom rule, we use tuples as the sorting key. The tuple is structured as frequency value, where the frequency is the first component, and the negative of the value is the second component. Using negative values allows us to achieve descending order for ties in frequency, as Python naturally sorts numbers in ascending order. The reason for using tuples is that Python's sorted function supports multi-key sorting. By placing the frequency first in the tuple, it gets priority during sorting, and the second key value is used to resolve ties. This approach ensures our sorting logic aligns perfectly with the problem requirements. Now that we have defined the custom sorting rule, the next step is to sort the array using Python's sorted function or the .sort method. We pass a lambda function as the sorting key, which extracts the tuple frequency_map x for each element x in the array. For example, given the input 4, 5, 6, 5, 4, 3, and its frequency map 4, 2, 5, 2, 6, 1, 3, 1, the sorting key for each element would look like this: 2, -4, 2, -5, 1, -6, 2, -5, 2, -4, 1, -3. When we apply the sorting, elements are arranged such that numbers with lower frequencies come first, and among those with the same frequency, larger numbers come before smaller ones. The resulting sorted array is 6, 3, 5, 5, 4, 4. Finally, this sorted array is returned as the output of the function. There are several key insights to take away from this algorithm. First, using a hash map to count frequencies is ideal because it allows us to complete this step in n time, where n is the size of the input array. Second, the custom sorting key, frequency value, is a powerful tool for handling multi-criteria sorting in Python. This method ensures that the frequency is prioritized, and ties are resolved by descending order of the values. In terms of efficiency, the overall time complexity of the algorithm is O(n*log n. This includes O(n) for frequency counting and O(n*log n) for sorting. Together, the algorithm is efficient and well suited for the problem constraints. The two main data structures used are a hash map, for storing frequencies, and an array, which is transformed into the sorted result based on the custom rule. When solving this problem, it's important to account for edge cases to ensure the solution works under all scenarios. First, if the input array is empty, such as nums equals, the output should also be an empty array because there are no elements to sort. Second, if all elements have the same frequency, like in nums equals 3, 1, 2, 4, where each number appears once, the output should be sorted in descending value order, resulting in 4, 3, 2, 1. Lastly, if there's only one unique element repeated multiple times, such as nums equals 7, 7, 7, 7, the output remains unchanged as 7, 7, 7, 7, since all elements are identical. These cases demonstrate that the algorithm is robust and can handle both simple and complex inputs effectively. To solidify our understanding, let's walk through a complete example. Suppose the input array is nums equals 4, 5, 6, 5, 4, 3. First, we create the frequency map 4, 2, 5, 2, 6, 1, 3, 1. This tells us how often each number appears in the array. Next, we generate the sorting key for each element, resulting in 2, -4, 2, -5, 1, -6, 2, -5, 2, -4, 1, -3. These tuples reflect the frequency and the negative value of each element. Using these keys, we sort the array to get 6, 3, 5, 5, 4, 4. Finally, this sorted array is returned as the output, fulfilling the requirements of sorting by frequency in ascending order and by value in descending order when frequencies are equal. This implementation solves LeetCode problem number 1636, sort array by increasing frequency, efficiently and concisely. Let's break it down step by step. 1. Counting element frequencies. We used the counter class from Python's collections module to count the frequency of each element in the input list nums. Frequency equals counter, nums, generates a dictionary where the keys are the unique elements of nums, and the values are their respective counts. 2. Sorting logic. The nums.sort function is used to sort the array in place, which is both time efficient and space efficient. The sorting key utilizes a lambda function, key equals lambda x, frequency, x, x. Frequency, x, this ensures the elements are sorted by their frequency in ascending order. X, if two elements have the same frequency, this ensures they are sorted by their value in descending order. The negative sign reverses the natural ascending order of numbers. 3. Return statement. After sorting, the modified nums list is returned as the output. Example. Consider the input nums equals 1, 1, 2, 2, 2, 3. Frequency equals counter nums results in 1, 2, 2, 3, 3, 1. Sorting by frequency x gives the order 3, 1, 1, 2, 2, 2, as 3, frequency 1, comes first, followed by 1, frequency 2, and finally 2, frequency 3. This solution is efficient with a time complexity of O, n log n, due to sorting, where n is the length of nums. The space complexity is O, n, for the frequency dictionary. The concise code ensures clarity and readability. Here, we begin by importing the necessary libraries, including java.util, which provides us with tools like hashmap and arraylist. Inside the solution class, we define the method frequency sort, which takes an array of integers as input and returns a sorted array. First, we use a hashmap to count the frequency of each number in the array. The key in the map represents the number, while the value represents how many times that number appears. Using the getOrDefault method, we initialize the count to 0 if the number isn't already in the map, then increment its count. Next, we convert the input array into a list to facilitate sorting, as lists provide more flexibility with sorting operations. Each element of the array is added to the list. Finally, we define a custom sort for the list. The comparator sorts based on two criteria, first by frequency in ascending order, and then by the number itself in descending order if the frequencies are the same. The integer.compare method is used to handle these comparisons cleanly. After sorting the list, we need to convert it back into an array to match the expected return type of the function. We use a simple for loop to iterate through the sorted list, assigning each element back to the respective position in the original nums array. This ensures that the sorted order is reflected in the output array. Finally, we return the modified nums array, which is now sorted by the specified criteria, first by frequency in ascending order and then by value in descending order for elements with the same frequency. This completes the implementation of the frequency sort method, providing an efficient and clear solution to the problem. To solve this problem, we aim to sort the given array nums based on two specific rules. First, numbers with lower frequencies should appear earlier in the sorted array. Second, if two numbers have the same frequency, the larger number should come first. For instance, in the input array 1, 1, 2, 2, 2, 3, the first step is to count the frequency of each number. Using Python's counter from the collections module, we find that the number 1 appears twice, 2 appears 3 times, and 3 appears once. With this frequency map, we can move on to sorting the array by defining a custom sorting key. The key ensures that numbers are first sorted in ascending order of their frequency and, for those with the same frequency, in descending order of their values. This is achieved using the lambda function, which returns a tuple, frequency, x, for each number x in the array. The custom sorting key we use has two components, frequent, x, to sort numbers by their frequency in ascending order, and x to sort numbers with the same frequency by their value in descending order. Let's apply this to the input array 1, 1, 2, 2, 2, 3. The frequencies of the numbers are 2, 2, 3, 3, 3, 1, and the sorting key for each element becomes 2, -1, 2, -1, 3, -2, 3, -2, 3, -2, 1, -3. Sorting the array using these keys results in 3, 1, 1, 2, 2, 2. This ensures that numbers are arranged first by frequency and then by value as required. The final sorted output for this example is 3, 1, 1, 2, 2, 2. Now, let's analyze another example. For the input 2, 3, 1, 3, 2, the first step is to count the frequencies. Using counter, we determine that 2 appears twice, 3 appears twice, and 1 appears once. Here, the frequency of the number 1 is 1, while both 2 and 3 have a frequency of 2. To sort the array, we again use the custom sorting key, frequency, x. For the original array, 2, 3, 1, 3, 2, the frequencies correspond to 2, 2, 1, 2, 2, and the sorting keys become 2, -2, 2, -3, 1, -1, 2, -3, 2, -2. When sorted based on these keys, the array transforms into 1, 3, 3, 2, 2. This result satisfies the problem's requirements, as 1 appears first due to its lower frequency, and 3 comes before 2 because they share the same frequency but 3 is larger. The final output for this example is 1, 3, 3, 2, 2. Let's now review one more example. For the input array 5, 5, 4, 6, 4, 4, 9, we start by counting the frequencies using counter. The results show that 5 appears twice, 4 appears 3 times, and both 6 and 9 appear once. From the frequency count, we know that 4 has the highest frequency of 3, followed by 5 with a frequency of 2, and 6 and 9 each with a frequency of 1. Using the custom sorting key, frequency, x, x, we proceed to sort the original array, 5, 5, 4, 6, 4, 4, 9. The frequencies correspond to 2, 2, 3, 1, 3, 3, 1, and the sorting keys are 2, -5, 2, -5, 3, -4, 1, -6, 3, -4, 3, -4, 1, -9. After sorting based on these keys, the array becomes 9, 6, 5, 5, 4, 4, 4. This ordering ensures that numbers with lower frequencies come first, and within the same frequency, larger numbers are prioritized. The final output for this example is 9, 6, 5, 5, 4, 4, 4, which completes the problem requirements for sorting the array by increasing frequency with ties broken by value. To analyze the time complexity of our solution, we start by breaking it into two main steps. First, we count the frequencies of each element in the array using the counter class from Python's collections module. This involves iterating through the entire input array, which takes n time, where n is the number of elements in the array. Next, we sort the array using Python's built-in sort function. The sorting process involves comparing elements based on a custom key, a tuple consisting of their frequency and their negative value. The overall sorting operation takes log n time, as sorting dominates the contribution of the key function, which itself runs in 1 time per element. When we combine these steps, the total time complexity becomes n for counting plus log n for sorting, resulting in an overall time complexity of n log n. Now let's examine the space complexity. First, the counter object stores the frequency of each unique element in the array. If there are k unique elements, this requires k space. In the worst case, when every element in the array is unique, k equals n, making this contribution n. Next, the sorting process uses Python's timsort algorithm, which requires n auxiliary space in the worst case. However, since the sorting is done in place on the original array, no extra space is needed to store the sorted result. Combining these factors, the total space complexity is dominated by the larger of k and n, which simplifies to n, because k, the number of unique elements, cannot exceed n, the total number of elements in the array. Let's compare this optimized approach with a naive one. A naive approach might involve manually counting frequencies by iterating through the array multiple times while storing results in a dictionary. Sorting such a dictionary would add additional complexity. For example, counting frequencies manually could take n squared time in the worst case, and sorting the dictionary items could take k log k, where k is the number of unique elements. This redundancy leads to inefficiencies. In contrast, our optimized solution leverages the counter class to count frequencies in n time and directly sorts the array in n log n, avoiding unnecessary data structures. This efficiency makes our approach significantly faster for larger inputs. Summarizing the complexities, the time complexity is n log n due to the sorting step, while the space complexity is n, as it accounts for the storage of the frequency data and auxiliary sorting space. These remain consistent across best, average, and worst cases since sorting dominates the overall complexity. When solving this problem, there are a few common mistakes to watch out for. One is forgetting to use a custom comparator when sorting the array. If you rely solely on the default sort function, it won't account for the dual requirement of sorting by frequency first and then by value in descending order, which is critical to meeting the problem's constraints. Another frequent issue arises with incorrect tie-breaking logic. Specifically, some solutions mistakenly sort values in ascending order when frequencies are equal, which goes against the requirement to sort these values in descending order. Additionally, modifying the array while calculating frequencies is a mistake to avoid. This can lead to inaccurate frequency counts or unexpected side effects, especially when using mutable data structures. Always separate these steps to ensure your solution is robust. Another mistake to avoid is inefficient frequency counting. For example, using nested loops to manually count frequencies can lead to an O(n)² time complexity, which is impractical for larger arrays. Instead, leveraging a hash map allows you to achieve this in O(n) time. Overlooking edge cases is also a critical pitfall. For instance, arrays where all elements have the same frequency or arrays containing negative numbers can break your solution if the sorting logic doesn't properly handle ties or account for negative values. It's essential to test against these scenarios to ensure your code is both comprehensive and error-free. Now, let's shift our focus to some interview insights. Hash maps are central to solving most frequency-based problems, so it's important to practice building and iterating over them effectively. Custom sorting logic is another must-know skill, as interviewers often test your ability to handle multi-level sorting conditions, just like in this problem. Additionally, discuss trade-offs in your solution, such as the time complexity differences between sorting and frequency counting, to demonstrate your analytical skills. Don't forget about edge cases. Always ensure your sorting logic can handle ties, empty arrays, and arrays with non-unique values. Finally, focus on explaining your intuition clearly. Many candidates lose points here, so break the problem into clear steps: frequency counting, sorting, and reconstruction, and articulate your thought process thoroughly. This problem also connects well with several related problems that you might encounter. For instance, LeetCode 451, which involves sorting characters by frequency, is a similar task but focuses on characters rather than integers. Another related problem is LeetCode 347, where you identify the top k frequent elements instead of fully sorting the array. LeetCode 692 builds on this idea but applies it to sorting strings, with additional tie-breaking rules specific to words. Lastly, LeetCode 75, known as Sort Colors, presents a simpler sorting challenge without frequency counting, but it's a great way to practice implementing custom sorting logic effectively. Finally, let's discuss some alternative approaches and their trade-offs. One option is bucket sort, which groups numbers by frequency and processes the buckets in the required order. This method is faster than comparison-based sorting, with a time complexity of O(n), but it's only practical for small ranges of numbers. Another method is using a priority queue or heap to store elements by frequency and then extracting them to build the result. While this approach can be efficient in terms of time, with a complexity of O(n) log k, it tends to be more memory-intensive. Lastly, there's the manual two-pass sorting approach, where you first sort by value and then by frequency in a stable manner. While easier to implement, this can be less efficient compared to combining the sorting steps. Each approach has its strengths and weaknesses, so consider which is most appropriate based on the problem constraints. That wraps up our discussion of LeetCode problem number 1636, sort array by increasing frequency. We summarized the approach, highlighted the key takeaways, and discussed its complexity. I encourage you to practice related problems to solidify your understanding. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!